All right, so today's lecture is going to be about particle filtering. So we've talked about, some different types of filtering before. Sorry, some different types of filtering before. We designed a Bayesian filter. We talked about motion and observation models, and then we discussed Kalman filtering, which is how do you do filter design when the dynamics and observations are linear Gaussian. Right? And so the only thing to remember from the Kalman filter is that dynamics are linear Gaussian, and you can use these special Gaussian identities to derive closed form updates for the measurement step and the dynamics step. Right? So like all you need to do is like take the formulas from my slide and just like code them up in NumPy, and then you can automatically implement filtering without needing to do any fancy stuff. Right? So it's like copy paste the formulas, but that only works when things are linear. And so today we're going to try and cover a method that is much easier than Kalman filtering, but is the basis of homework 2, right? And so it's called particle filtering, and it's going to be a lot easier to implement with what you're going to run on the cars. So pay attention. Like last lecture was mostly about vibes. This lecture you want to pay attention to. Yeah. Okay. So some logistics. We'll release homework 2 this evening. It's the longest homework probably, so we pushed it back 2 days. So you have a few more days to finish it. Next Wednesday, we're going to have these paper presentations. And so there's going to be basically 2 teams will present 1 paper each. And I emailed the people who are presenting already, and I posted an announcement on EdStem, but those are the papers we're going to be reading if you want to look them up. And we'll post a thread on EdStem, and everyone else in the class who's not presenting should just like answer the questions in the thread after reading the paper, right? And so you'll have some small amount of grades on that. And then we have 4 of these, so we'll try to circle through all the teams that we have listed. Any questions? And my EdStem thread will have a set of like what I expect to see in a presentation. Yeah. Okay, great. So what we're going to do today is we're going to start by talking about what I mean by particles. Like we have a particle filter. What the hell is a particle, right? And then we will try to we'll try to understand what particles are. We'll instantiate a filter with particles, try to make a practical algorithm out of it. Then we'll try to fix some of the issues with this filter, which make it not practical to use. And then we'll deal with like practical considerations during implementation, which will make everything efficient. Right? And you need all of these pieces for your homework. So make sure you go back to this lecture and review it and so on, and come to office hours if you need more help. Okay, so to go back to the start, it's our standard Bayesian filtering. We have our prediction step, or dynamic step, correction step, or measurement step. This is incorporating an action. This is incorporating a measurement, right? And so this is what we've been discussing for the last 4 lectures. And last class, we tried to instantiate this model with the dynamics model being linear Gaussian and the measurement model being linear Gaussian, right? And that we saw was kind of a pain, but it gave us like these nice closed form formulas that we can apply and everything works good. The problem with that is that the world is not linear, right? And the world is not Gaussian, right? So like typically you don't have functions that are Gaussian like that. You have functions that are not Gaussian, and the dependence of the past states and actions is not linear, right? So for instance, in the motion models and sensor models, things that we saw, right? We had an exponential, we had a cosine, we had a tangent, like those are not linear, right? And so the point is that the dependence on previous state and previous action is neither linear, and the functions are not Gaussian, right? So all of the stuff we discussed in the Kalman filter doesn't really work because you're not linear and you're not Gaussian. So what do we do? We're kind of screwed, right? So what we're going to do today is we're going to try and discuss a much easier way where you can replace, special form functions, which is brute force computation. And brute force computation is going to make everything easier, right? So the key idea behind particle filters is to just replace special types of functions with like lots of computation. Lots of computation, lots of memory, right? And so the thing we're going to try and figure out today is like, how do we do Bayesian filter when you have measurement models and sensor models which are not linear and not Gaussian? So what I mean by not linear is that the dependence on ut and xt minus 1 is not linear. Like last time we saw it as linear. And the dependence on in the measurement model on xt is nonlinear. And the form of the probability distribution is not a Gaussian, right? Okay. Any questions on the issues here? Like, why should we study particle filters? Okay. So what we'll cover this class is how do we do it with brute force computation? And what we'll study next class is how do we solve it by trying to convert nonlinear problems into locally linear problems. Like, does everyone know how the Taylor expansion works? The Taylor expansion tries to take a nonlinear function and write it as a locally linear function. And so the trick we're going to use in the next lecture is not through computation, but through local linearization, right? And so today we're going to do brute force computation. So the issue is that, we have this target distribution, which is non-Gaussian, and we want to, approximate with a Gaussian. That's bad. And typically, you're going to lose expressivity. You're going to get things that are inaccurate. When you introduce this approximation, you drop modes, bad things happen. And so we want to get away from the Gaussian assumption. And the key thing we're going to notice is that you typically don't care about actually having a closed form of the distribution. Like, who cares? What you want is samples from the distribution. So if you have a distribution of where I could be, I don't need to know the likelihood. I just need to have samples of where I could be. Right? So if I have some sort of method to sample many different samples of where it could be, that's usually enough, right? And so typically what you want to do, for instance, the reason you want to maintain uncertainty, right? So you want to say, I could be here, I could be here, I could be here. You want the average performance to be pretty good, right? And so the problem with being having a point estimate, collapsing uncertainty is you might be overly confident in the wrong place. But the reason you want a distribution is not just for the distribution's sake, but it's to compute averages, right? So in the next parts of the class, you're going to do planning, you're going to do control, and there you want to say, okay, average performance under the distribution of states should be pretty good, right? And so the trick we're going to use to get away from the Gaussian assumption is the fact that you don't need the distribution, you just need averages, right? And if you want to compute averages, you can usually do it with just having samples. And by samples, I mean just imagine that you had a bunch of points where you could be, right? And that's a sample. And so you want to move away from closed form distributions. Everyone follow that? Motivation makes sense? Okay. So typically you want to do things like compute the mean position, compute the probability of collision. You want to compute the value function, which is what is the expected cost in the future, right? And so you want to, you never want to actually deal with the probability distribution. You want to use the probability distribution to compute some averages, right? So for our car, we might want to minimize the probability of collision, or we might want to, minimize the cost to go, or the average cost to go, right? In all of these cases, you just want an average. And the trick is that averages can be estimated by samples. That's the whole trick. Okay. So there's this idea called, that's Monte Carlo. But there's this idea called Monte Carlo estimation, right? So Monte Carlo estimation, all that it means is that if I have a probability distribution and I don't know its closed form, but I can sample from it, I can replace averages with sum over samples, right? So imagine that I didn't know the probability distribution, but I was able to draw samples from it. You can replace an integral with an average over many, many, many different samples. Yeah. And so essentially what Monte Carlo simulation is saying is that if you have some belief distribution and you don't know the belief distribution, but you have a bunch of samples from it, right? You can compute the expectation by just taking an average of those samples. And so the point is you don't have to weight the samples, you don't have to do anything, you just literally take an average of the samples. And in areas where you have high likelihood, those samples will occur more. Areas where you have low likelihood, those samples will occur less, right? So you automatically get things to be weighted. And so the idea is if you can draw samples from a distribution, you just weight that, you just average them unweighted, and then you get an average under that distribution. Right? That's the whole idea behind Monte Carlo simulation. It's arguably the most impactful thing in science in 30 years. Not 30, 50 years. So we use it all the time in machine learning, we use it all the time in robotics. And so that's the key idea. Does that make sense? So the point is you don't need closed form distributions. You don't need to know the likelihood of anything. Right? If I can draw samples from something, then I can get expectations of it. That's super easy. Now, can someone give me an example where this is useful besides robotics? Like, why would I, in what case would it be, hard to know the likelihood, but maybe easy to generate a sample? What do you think?
Well, just generate these examples.
When is it easy to generate? When might, like, give me an example application where it's easy to generate samples, but it's hard to know, like, probability distributions. Okay, I'll give you this. So an example is through like a lot of these big national labs, right? They have these like huge scientific models of how atoms interact or how molecules interact with each other. And you need to like, they have these complex equations that specify how atoms interact with each other, what forces they apply, and they do it probabilistically, right? But the point is that you have to run this really, really expensive simulation through this like complicated nonlinear equation function thingy. So it's like really hard to get a closed form. But you can, like, you're running it on a data center, so you can generate a lot of samples. So a lot of times in science, when you want to compute some average quantities, right, you can do it through Monte Carlo simulation, even when you don't have closed form, right? So in cases where your like simulator is very complicated and it's hard to get like closed form, but you can generate samples, this thing is useful. Does that kind of give you some intuition? Or imagine that you're a robotic simulator. It's like this complex physics equation thing, lots of cosines and sines, and it's very hard to like do things, but you can run simulator.step. Simulator.step takes you forward. It gives you a sample. So it's like easy to generate samples, hard to get likelihoods. Does that make sense? Okay. So that's the key idea we're going to use. So here's an example, right? So you have this area, which is like 1/4 of a circle. Okay. Now you know the formula to compute the area. What's the area going to be here? It's a unit circle. What's the area going to be? 5, right? But an easy way to do it, a different way to do it, is to say you're just going to throw a bunch of darts at the board, and then you're going to measure which ones lie inside the circle versus not, right? And so you sample points uniformly from the unit square, and you check how many of them are inside, and then you take the average of that, and you will see that that gives you the same number. It gives you pi/4, right? Try it at home. It's easy. But the point is that you could have computed things in closed form, but you can also just compute things by sampling brute force, blasted, right? Now, when would this not work? Like, when is this going to be bad? When is the estimate going to be bad? When you don't have many samples, right? You don't have many samples. So often the tricky part here is the n has to be super large. Right? It's only true in n tending to infinity. Okay, so those are the pros and cons, right? So we have this concept of Monte Carlo simulation representing distributions by samples, right? So what that means is that any distribution that you have, right? If I can compute its expectation by a set of samples, I can almost like replace that distribution by a set of samples, right? Like everything I want to do with that distribution is now replaced by the samples, right? Because all I want to do is compute averages. So if I have the distribution, just keep the samples around, it's equivalent. Yes. So what we're going to do is in our Bayesian filtering update, right? All we're going to do is for all our probability distributions on belief, instead of representing belief as a Gaussian or a particular probability distribution, you're going to represent belief as a set of particles, right? As a set of samples. You're going to call those particles, but it says that, if some areas have high likelihood, you're going to have more samples there. Some areas have low likelihood, you're going to have less samples there, right? And so the point is that I can now completely replace a belief by a set of samples, which you're going to call particles. Yes? Okay, so a question for you all is, okay, so let's say I replace belief by a set of particles, and my state space is, position, x, y position, and heading, right? What are the particles, what dimension are the particles going to be? Three. X, Y, heading.
I thought you said X, Y position heading.
So yeah, but what else? The number, like the point is that each of the particles is the same dimension as the state. right? So it's like, imagine you had a set of things, each of them is like a state, right? And like in places that you have high likelihood, you have more of those things in your set, right? And so you're going to just replace a distribution by a set of states. That's the whole idea of particle filtering, okay? And we're just going to try and make it tractable from there. Yes? Simple? No Gaussians, no math, no nothing. Yeah, very easy. So let's try and work through, our Bayesian filtering equation. Our standard Bayesian filtering, you have this recursive update, right? You have the dynamic step and the belief step and the measurement step. And now we're going to try and instantiate this in terms of the particles, right? So we want to answer two different questions. One of them is that if these were a set of particles, right? And you want to, do this integral with the dynamics model, how do you decide the particles at the next step? Okay, so belief was a set of particles. Belief bar is going to be a different set of particles. How do you decide what the particles at belief bar are going to be? Yeah, that's the first question you're going to ask. How do you sample from the product of two distributions? You have two distributions multiplied. You have particles here. These are also going to be particles. How do you decide which particles will be in belief bar? That's question one. Question two is, okay, now you have some particles in belief bar. You want to incorporate the measurement, right? In order to get some different particles, which are going to be belief. Right? And so how do you go from belief bar to belief? How do you incorporate measurement into these particles? Does that make sense? So those are two questions you want to answer. If we know those two questions, we can implement the dynamic step and the measurement step. Everything is going to be in terms of particles. And then everything that you want to compute, like averages and sums and stuff, you just sum up those functions over those particles. So if you want to find the mean position, take all those particles, average them. If you want to find the cost, take the cost of each of those particles, average them, right? And so you can do everything you want with those particles. So we just need to answer these two questions. Yes? With me? Okay. Okay, so that is the representation that we're going to use. We're just going to use sets of states. Now we're going to instantiate your particle filter. Right, so let's start by thinking about the dynamic step. The dynamic step is taking your previous belief, multiplying it times the likelihood of moving forward, and then integrating it over all of the states, right? So this is a thing we've seen in the last 3 lectures, just moving forward through time. And the question is, how do we sample from the product of two distributions? So if this was your previous set of particles, how do you decide your next set of particles? When you know your dynamics model, okay? So you want to know your dynamics model. Let's say you had a simulator for your dynamics model. Okay, so you knew xt minus 1, ut minus 1, you could stick it into a function, and that function would generate an xt for you, right? Probabilistically, you have an xt minus 1, a ut minus 1. It goes into your function. The function gives you a new sample at the next step. That's a bad code, actually. But so you have this function. It doesn't need to be Gaussian, right? It doesn't need to be Gaussian, and it does not need to be linear. You just need to be able to take in a function, a black box function that takes in xt minus 1 and ut and generates x. Right? Okay. So you can probably guess the answer. You have a previous set of particles. You have a black box function that can take in a state, an action, and give you a new state according to the dynamics model. How do you get the new set of particles? Not a trick question. Right? Put it through the function. That's it. That's it. So treat each particle as a point estimate. So imagine you have a set of particles, right? Take each particle, right? This is your set of particles. Take each particle, stick it through your dynamics function with the action. It gives you a new particle. And that is, you're going to do that for every single particle in the space. So you get a new set of particles, that's your new set. So you can almost think of it as like, this belief is a set of particles. For each of those particles, you send it to your function, gives you a new particle, that is your new set of particles, right? So imagine that this was your set of particles, and your dynamics model says everything moves to the right. What's going to happen? All of these particles are going to move to the right, and as a result, your probability distribution moves to the right. Yes. Can you repeat?
How about the noise?
It's a good question. That's a good question. So what about the model? Right? So the nice part is that your dynamics model is going to sample things with noise. It's not a deterministic function. It's going to say, It's going to say taken xt minus 1 ut, give you a new state, and then add some noise to it, right? So the particles are going to be generated with noise, not deterministically. So this distribution, this function is not a deterministic function. It's going to be a stochastic function. So in your homework, you'll have a stochastic function that takes in a previous state and action and gives you a new state with some noise added, right? That's how it happens. Good question. Any other questions here? Okay, so let's look at some examples and try to see if this becomes more clear. So let's say you have this robot. It's trying to figure out where it is in the hallway. Okay, it doesn't know where it is. There's these 3 doors, and you can hear noise behind some of the doors. And those are the measurements. It has some belief over where it is. And what we're going to do is we're just going to, move the robot. And the robot is going to move. You're going to have some motion model which tells you where to move all the particles. And so now all the particles move. Right? And so all these particles are just gotten by taking the previous set of particles, sticking them into your motion model, your dynamics function to get a new particle, new set of particles, nothing else. So you take away anything from the last 5 minutes, just like this line is the only important. Take every particle in xt minus 1, stick it through your dynamics model. It gives you a new particle. You've done the dynamic step. Much better than Kalman filtering. Right? Kalman filtering is a waste of time. But this tends to work pretty well. Why might it not be hard? What makes it hard? Like, why is this not the solution to AI? You need a lot of particles. That's it. So to make an accurate average estimate, you might need a shit ton of particles. Imagine that your state was 1,000 dimensional, you need exponentially more particles, right? And so it depends on your problem, but on low dimensional problems like navigation, this tends to work super well. Okay, so your dynamics update, no Gaussian, no linear, just push forward. Those are your previous particles. You stick it through your black box function, give you some new particles, you've done, right? So we've solved our linear and Gaussian problem for the case of the dynamics function. We're going to follow that? Simple, right? Okay. Now, the rough part is that it's like trickier to incorporate the measurement, right? So when you have the measurement, you have this like normalizing constant, which is difficult. You don't want to just push things forward. You want to incorporate the measurement and readjust the belief according to the measurement, right? So it's not so obvious how to do it, right? And so if you write out the measurement step, that the measurement step is going to take your belief bar, multiply it times the likelihood of a measurement P of zt given xt, and then have a normalizing factor on it, right? Because it needs to be a probability distribution. Okay, so if we expand out the normalizing constant, right? The normalizing constant is just going to be an integral of the numerator, right? So that the whole thing integrates to 1. You need probabilities to integrate to 1, right? So you can write this thing as P of zt given xt by integral P of zt given xt times belief bar. Now, the nice thing here is that you can almost think of this P of zt given xt divided by this integral P of zt given xt as like a weight. So imagine that you had a bunch of particles, and this entity, which is P of zt given xt divided by a normalizing constant, is like a weight for those particles, right? And so if you want to get, you had a set of unweighted particles at belief bar. To get the set of particles at belief, which are representative, you can represent the distribution by a set of weighted particles. So you no longer just have a set of particles, you have particles and weights. Right? And then those weights are basically P of zt given xt divided by the normalizing constant, right? And so you can almost think of this as, let's say you have a finite number of particles, you can think of the weight as P of zt given xt divided by the sum of pt given P of zt given xt for all the other particles. Right? And so what this is saying is that you had a set of unweighted particles at belief bar. To get the set of particles at belief, you're going to take the same set of particles, and then you're going to weight them by P of zt given xt by sum of P of zt given xt. Okay, so maybe this becomes clear with, let me see if I can find a little picture for you guys. Okay, so this was your set of particles that you got from the step from belief, the previous belief to belief bar through the dynamics. Okay. So now your distribution is represented by these set of states. Okay. So they have a set of states, and you want to incorporate measurement. You want to incorporate measurement. So what you're going to do is you're going to take this weighting function, which is P of Z given X divided by sum of P of Z given X, right? And that is going to be the weight for every single particle, right? And so you can think of the particles which are more likely will have a higher numerator, and the particles which are less likely will have a lower numerator, right? So the particles that are most likely will have highest weight. Think of the size of the circle as the weight. And particles that are less likely will have less weight. Right? So you can, now you've gone from a set of unweighted particles to a set of weighted particles. Right? Does that make sense? It's a little bit weird. So it's like, we've talked about, so far we've talked about everything being unweighted, right? So it's like all averages are just unweighted sums of X or F of X, right? So you have some, let's say you had a set of particles, x1 to xn, right? You want to compute some average of this with some function f of x. You're just going to say, okay, we're going to do 1 over n f of xi, I from 1 to n, right? That's how we computed the average. This is when you had unweighted particles. Now, when you have weighted particles, each of these is associated with a weight. Okay. And now your average is going to be 1 over n just a weighted sum, right? And so I'll derive why this is not random in a second, like this is principle. But practically what you want to say is, okay, if we had a set of particles before, to get a set of particles after the measurement, we're going to take the previous set of particles and multiply their weights by that WI factor, right? So initially the weights were all 1. We multiply by the WI factor, things that are more likely under the measurement, right? So if I was like right next to a wall, I received a measurement, it's likely that I was here, it's less likely that I was there. So the particles which are here will get higher weights, particles which are there will get lower weights, right? That makes sense intuitively? Yes? No? Sorry.
How about the particle? It's not. It's natural.
Right, like that particle is not even in the set of particles. Yeah, that's going to be a problem. And we will, I'll discuss that in a second. So a problem with this initial version of particle filter, if you don't have enough, if you have particles everywhere, then you're good. But if you don't have particles there, like you'll never get weighted. Right? So the problem with having a small number, like you might need an immense number of particles to actually represent that. So that's going to be a problem. Oh, like let's say you wanted to compute some average. Let's say you wanted to compute average cost or the average position, the average, like whatever you want to do downstream with your business, right? So like the reason you want particles is so that you can compute downstream quantities, right? And so let's say this was cost or average or like probability of collision or position or something. Like it can be any function. Okay, so remind me of your name, the back. Okay, yeah. So Sherry brought up a really good point about if there's no particles in some places, you might be totally screwed. And we'll correct that in a second, right? But the point I want to make here is that you can, the way you incorporate measurements is to go from a set of particles that you had before and multiply them by a weight function. And the weight function is the likelihood of the measurement divided by the sum of likelihood of the measurements under all the particles. And so you go from unweighted particles to weighted particles. And when you repeat this over many steps, you'll have the weights being multiplied, right? So it's like you started with unweighted particles, then you move them forward, then you weighted them, then you move them forward again, and you weight them again, you move them forward again, then you move them. And so that's going to be a problem, and we're going to discuss how to fix it, right? But the idea is that you alternate between moving the particles forward and weighting them. So correction step is weighting, dynamic step is moving things forward. Yes? At least mechanistically, do you guys understand why this makes sense? Or mechanistically, do you understand how to do this? And then we'll discuss why this makes sense. Yes? Okay. So it seems kind of random to do this weighting thing, right? So you can explain what we're doing in this weighting thing by this idea called importance sampling. And in importance sampling is asking, how do you sample from a particular complex distribution P when you don't actually have samples from P, but you have samples from Q. So let's say you want to get the average of some function under P. You want to take the expectation under P, but you don't have samples from P, you have samples from Q. Then how do you try and compute the expectation under P if you don't have samples from P, right? That's the question that importance sampling is going to ask. Doesn't seem connected right now. We'll try and connect. Okay, so what importance sampling is going to say is that you want to sample from an easy distribution, which is Q. And then you want to reweigh the sample so that it matches a target distribution that is hard, which is P, right? So it's saying that imagine that you had a bunch of samples. Imagine that you don't know how to sample from this target, but instead you had a bunch of samples from this proposal. Okay. So the proposal distribution is Q. The target distribution is P. You want to compute the average or the expectation under P, but you don't have samples from it. You just have samples from Q. And the magic you want to figure out is how to get the expectation under P just using samples from Q. Right? That's the question. And we're gonna connect it back to our weighting thing and explain it, but does the premise of importance sampling make sense? Right? Computing the average under P only using samples from Q. Okay, so the way we're going to do it is you're going to like sample a bunch of things from your proposal distribution, your easy distribution, and then you're going to re-weight them. And you're going to show that a weighted sum of samples from the proposal distribution gives you an average under the term. Okay. And so now it's starting to sound a bit more like our correction step, right? So what we're going to show is that expectation under P can be given by a weighted expectation under Q. Okay, so let's look through what the math looks like. So what we want to compute is the average of some function f under P, right? This expectation of f under P, average, right? Average of sum of f weighted by P, right? That's what the expectation is, just the average. Now you're going to do a simple trick, multiply and divide by Q. Yeah, just multiply and divide by Q. And now move the terms around a little bit, right? Move this Q over here, move this P over here, right? And so now you can write this as Q times P over Q times F, right? Everyone following me so far? And now you can noting what the definition of the expectation is, right? What is the expectation of x from P of F? It's just the sum of P times F, right? So this thing is just the expectation under Q. You can think of this thing as the probability, and if this thing is the thing inside the brackets, right? So you can say that, let me write it so Zoom people can see too. You can think of, you can think of this thing as an expectation of this inner quantity with respect to Q, right? So the way you can derive this thing is equal to this thing, expand the expectation, multiply and divide by Q, move Q to the other side, and then note that this is the average of this weighted quantity with respect to Q. Right, so you can rewrite this whole thing as expectation under Q of P over Q times F. So if I can compute P over Q, then I don't need samples from P, I just need samples from Q. But they're weighted samples, right? So they're no longer F, it's F times a weight. Okay, that's the whole idea of importance sampling. Everyone following me? Now, I haven't told you why it's useful. This is like a random thing that I told you, but we'll call this thing an importance weight, P over Q. And what I need to compute is P over Q in order to, if I want the average under P, I just need samples from Q and the ability to compute P over Q. Yes? Everyone believe me here? What do you think? Does that make sense? Lost. Okay. Tell me which part is confused. Yes, I'll connect that in 1 second. So, okay, so why did we do importance sampling? Is because we had a distribution belief bar. Okay? We had a distribution belief bar, bunch of samples, bunch of particles. And you want to do this measurement step. And so you want to have the measurement step, you want to incorporate this thing, but I don't know how to incorporate this thing. I don't know how to compute averages under that thing, right? So what I want to do is compute averages under this thing using this thing, right? So easy distribution, hard distribution. Right, so this is the proposal, and this is the target. Right, so I want to compute the average under P, but I only have samples from Q. Yes, and so the reason you want to do this important sampling stuff is so that you can explain how to go from belief bar to belief. Yes, so what you want to say here is that imagine I had samples from here. How did I get samples from here? How do I get samples from belief bar? We talked about it for like 20 minutes. Not big, no important sample, yeah. Push everything through your dynamics model, right? So we push everything through your dynamics model. You had a bunch of samples, you pushed it through. Now you have a bunch of samples from belief bar, right? And now you want to go from belief bar to the belief at the next time step. That's where we're stuck, right? So you want to go from belief bar to belief at the next time step. And I'm trying to motivate why we need to do this weighted particle stuff, right? And so you can think of it as, okay, we went from previous belief to belief bar by pushing the particles through the function, a bunch of particles, right? And now what we want to do is we have a bunch of samples from belief bar. We push them through. Now you want to be able to compute averages under belief at the next time step, but you don't know how to compute it, right? So what we're instead going to try and do is try to compute averages under belief, which I don't know how to compute, using an easier distribution, belief bars, which I do know how to compute, right? So you spend all this time going from the previous step to the next step, right? And that gave us a set of particles for a belief bar. So I know how to compute averages when I know samples. I can compute averages. I want to be able to compute averages under that hard distribution from this easy distribution. That's where we're at, okay? And so now what you're going to do is divide P and Q. Okay, so you have the hard distribution and you have the easy distribution. Like we saw in important sampling, you want to compute the average under P, you can take the average under Q, but just weighted by P over Q. If you can weight it by P over Q, then you know how to compute the average under P, even if you just had samples from Q. Everyone following me? Okay, so let's connect it back together, which is, okay, actually, let's just go over this again. So, what this is going to say is that once I know this weighting function, right? If I associate every one of the particles with a weight, to compute averages under P, I just need to take averages under those particles, multiplied by the weight, right? So just like the important sampling derivation over here, to compute the average under P, you take the average under Q and just multiply by the weight, right? That's what we did here, right? We said the expectation under Q is, the expectation under P is the expectation under Q multiplied by some weight. And so what we do now, to go back to Bayesian filtering, is to go from belief bar to belief, right? You just try to compute this weight, right? Which is just going to be measurement likelihood divided by sum of measurement likelihood. That's going to give each particle a weight. Does that make sense to everyone? Okay, we'll put everything together and we'll get rid of the fluff. But I just want to make sure that it's not like super arbitrary, right? So what's going to happen is that after the step where we took the dynamics, right? So we moved somewhere, we got a set of belief particles, right? So we moved, these are the particles after the beliefs, after going from beliefs to the previous step to belief bar, okay? So we did the dynamic step, we got a set of particles. Now you want to figure out how to weight the particles, right? So we've said that you need to compute the weight by the likelihood of the measurement divided by the sum of likelihood of the measurement, right? So now you're going to have the same set of particles, but the y-axis is going to tell you the weight of the particles. So some particles are going to have high weight and some particles are going to have low weight. So the dynamic step was take previous particles, stick it through this function, gives you new particles. The measurement step is take those new particles that you have, weight them by the measurement. Right? So like take the measurement likelihood, average them, and that gives you the new set of weights. Right? So now you have a weighted set of particles. And to compute the average at any point, you just take the weighted sum with respect to each of those, like Wi times f of xi. Right? So at any point, you're going to have a set of particles, x1 to xn, right? And you're going to have a set of weights, w1 to wn. And to compute the average at any point, you're going to take the sum of wi f of xi. For any f, Like you want to compute the average cost, you want to compute the average position, you want to compute any averages. You just keep these weights around, and to get the average under the latest belief, you just keep the weights to Wi times f of x. Okay, now's a good time for questions. How are we feeling about this? If you don't understand this, you're gonna fail the homework. So you better ask me the questions. Yeah.
Start with some protocols, we push it for motion.
Yeah.
And then we generated a set of weights, but we're not using those to change our set of particles.
Correct. So we're gonna fix that. That's gonna be a problem. So the point here is that what you do is you keep accumulating weights. So think of it as you start unweighted, you move something, and then you change the weights. And then you run dynamics again, so you move the particles again, but keep the weights. And then you weight it again, so the particles get weighted again. So it's almost like unweighted, move, weight, move again, weight again, move again, weight again. Right, so it's like, imagine that you have a slide for this somewhere. One sec. Okay, so this is how the step is going to go, right? So you start with an initial set of particles. You're going to move them with the dynamics method. So you're here, move the particles. Okay. Then you're going to run the measurement step. So those set of particles is going to become a weighted set of particles, but the same positions. And then you're going to run the dynamic step again. So all of these particles is going to be moved somewhere else with the same weights. Then you're going to run the measurement step again. So the previous weights are going to be multiplied by the new weights. So you get it, or you stay in the same position, different weights. And then you run dynamics again. So the dynamic step moves where the particles are, and the measurement step just reweights the particles. Does that make sense? Yeah.
How do you figure out where the particles are initially?
Usually you want to have like, it depends on your initial belief, right? So it's like, if I believe that if I have no idea where they are, I just spread them out uniformly. If I kind of know that I'm in that corner, I put like particles there. So it's like a bit of domain knowledge. If my explanation make sense to you? Yes. Okay. Let's go through it slowly, right? Because it's important for you guys to understand. So help me understand which part is unclear. Is it about the motion of the particles or is it about the weight? So think of it this way, right? So you had a bunch of particles, okay? So you had some particles, yeah? And then you're going to run dynamics. So dynamics is going to say, okay, particles will move to different places. Okay. So that's step one. And then you have another step, which is going to say, okay, this is going to be measurement. And the particles are going to remain in the same place, but they're going to get different weights. Okay. And now you're going to have another dynamic step, the next dynamic step, right? And the next dynamic step is going to keep the same weights, but it's going to move the particles. Same thing that you did before. You like stick the particles into the function, it moves them, right? So you said particles move, they get weighted, and then they move again, right? And now you're going to like weight them again. So you're going to have measurement. And then the measurement is going to say, okay, like this, each of them are going to get multiplied again. So you might have like, oh, sorry. What's going to happen here is you're going to have like maybe same positions, but different weights, right? And then the dynamics is going to move them again. And the measurement is going to reweight them. And the dynamics is going to move them again. The measurement is going to reweight. So the weights just carry over. So like, imagine I stuck in a particle to the dynamics function. The dynamics function said, hey, your particle is now going to be here, right? So you're going to get a new particle in a new position, but it's going to have the same weight that it had earlier. So it's going to be like, this thing, let's say, had a weight of 5, or not 5, 0.1. Now it moves here according to a function, it's going to retain the weight of 1. Whereas another particle had a weight of 0.5, it moves here, it's going to retain the weight of 5. Right, so the dynamics function moves the particles without changing the weight, and the weighting function reweights the particles without changing their position. So you alternate between moving, reweighting, moving, reweighting, moving, reweighting. Does that make sense? Okay. Yes. It's not, nowhere is a Gaussian. It's just a set of particles. So nowhere is anything Gaussian, right? So it's just like, nowhere have we assumed anything to be Gaussian, right? So. That's it. Let's like for instance, in the sensor model lecture, we said that it's like a mixture of an exponential thing plus a uniform thing plus a Gaussian thing. Right, so you can have at any probability distribution, you just need a number, because just a weight, right? So you don't actually need to have it be Gaussian, you just need to have a number for it, because it's just going to give you. Okay,
So that function is given by this, right?
sensor model, yes, yes, so this is your motion model, and this is going to be the motion model, this is going to be the sensor model. Right, so the reason we covered them is so you can stick them in like here. Okay. Yeah, more questions, it's fine if we go slow, no problem. And we'll make more time for the homework if needed, but I want everyone to understand it very well, yeah.
For the importance weight we're
Yeah.
talking about, the P is the hard.
Our distribution, yeah.
Yeah, but we still have piece of sample on to get P, like, to get to, but P over P.
So the nice part is you don't need to sample from it. You just need to know what P over Q, the number for P over Q is. So like, imagine you had a distribution, like for instance, nowhere do we need to sample from this, right? So let's go back to importance weighting, right? Here, right? You don't actually need to sample from it. I don't need to generate a sample from P. Like when I have a distribution, a sample means that I have to generate an X, right? I don't have to generate X. I need to generate X from Q. And then I need to be able to evaluate what is the likelihood of X under P. So I need to stick X into the likelihood function to give me a scalar. It needs to give me a number, right? So it needs to tell me what the probability is that I would get X, right? And if I can get the probability of P and Q, then I can just divide them. Now, that's not always easy, right? But in our special case, when P is belief and Q is belief bar, you divide P over Q, right? Then you get that P over Q is belief over belief bar, which is just eta times P of ZT given XT, which is something that you can compute. Does that make sense? So you don't actually need to sample from P, you just need to sample from Q, and you just need the ratio of P and Q. Make sense? Okay, any more questions? Yeah. Yes, that's the measurement model. That's like the sensor model, that's the laser beams, the previous stuff, right? So P of ZT given XT is laser beam model. P of XT given UT XT minus 1 is the like physics, cosine, sine, car model, right? So we know exactly what this is. We know exactly what this is, so everything is computed. Like that, like the physics stuff we worked out is going to give you literally going to do this. Yeah. And the measurement model that we compute is literally going to do this. And so you know this, you know that you can compute. Right? So to kind of like put this section in some context, let's go through an example, okay? I know we're running late. Let's see if I get this up. So we're gonna start with a set of particles, okay? So you're gonna, let's say you had 3 particles. Their weights were 0.5, 0.25, 0.25. Now you're gonna run one step of dynamics, right? So dynamics is gonna say, we're gonna move where the particles are, but we're not gonna change their weights. Let's say move the particles, you have not changed their weights. And measurement is gonna say, hey, you're gonna take a measurement, right? So you shot some LiDARs, you saw some walls, right? You got some measurement readings, and the measurement is gonna say, let me take the previous weights and multiply them by my measurement likelihoods, P of Z given X, right? So I'm gonna get a set of new weights, right? And I have to renormalize the weights so that they sum up to 1. The weights always have to sum up to 1. So I'm gonna say, measurement model, move the particles without changing the weights. Dynamics model, move the particles without changing the weights. And the measurement model kept the particles in the same place, but changed their weights. Right? So you alternate between moving particles with the same weights, reweighting particles without moving them, and repeat. Right? So you can run this, and now you're going to have a new set of particles which are in a different position than the initial stuff. So you did dynamics, you move it, you weighted them with measurement, you renormalize. So these things sum up to 1 again, right? But they take the measurement into account, right? And so you keep repeating this. So you propagate the weights and you propagate the particles. Does that make sense? Okay. And so now you have a new set of particles. And anytime you want to compute any averages, right, you can just keep the particles around And like, let's say you want to compute some average of some f of x, right? You take f of x at each of these particles and take the weighted sum of them. That gives you the average. Yes. And the reason to, like, you don't need to really remember the importance sampling, it's just a nice way to derive it, right? But the real thing you want to remember is this loop, right? You want to start from the initial set of particles, move the particles while keeping the weights, change the weights while not moving the particles, renormalize, repeat. Yeah.
So the important stuff is populated by the measurement.
Sorry?
So the measurement.
Yeah.
is the importance weight.
The importance weighting is a way to derive why the measurement makes sense.
Oh,
So the importance sampling is not important. It's just like a way for us to justify why we did that, which is not crazy, right? And so importance sampling goes into here. The dynamics model goes into here. So move and then reweight, move and reweight, move and reweight, right?
so we want you to find another easier.
No. Yeah. So the nice part is you can be nonlinear, non-Gaussian, and you'll be good. Okay. We will cover the rest of this on Monday, but I will have some more notes for you. Okay. And if you don't understand, just stop by after lecture. Let's talk more about it. Thank you.